Okay, we're going to start Module 4. In Module 3, we talked about direct proofs and proving something directly. Module 4 is going to be about indirect proofs. So there's two types of indirect proofs we're going to talk about, proofs by contradiction and proofs by contraposition. And both of them approach proving something indirectly. So let's start with an example about the Knights and Knaves. So remember the Knights and Knaves problem. You find yourself on a desert island filled with knights and knaves, where knights always tell the truth and knaves always lie. There are no alternatives. A knave can't sometimes tell the truth. They always lie, and knights always tell the truth. You meet three people, A, B, and C, each of whom is either a knave or a knight. A says that all of us are knaves, and B says exactly one of us is a knight. We want to figure out what are A, B, and C. Well, let's brainstorm a little bit here. The way I like to solve these problems is we have a bunch of choices, right? A could be a knight or a knave. B could be a knight or a knave. C could be a knight or a knave. Let's start by picking one. I'm going to start with A. A says all of us are knaves. Well, we could suppose that A is a knave, in which case, and see where that led us. But I'm going to try saying, what if, suppose A were knight? And I'm picking knight because I think it seems like that will be easier, because if A is a knight, then what does that mean? Well, that means the statement that all of us are knaves would have to be true, but we said A was a knight. So we've run into a contradiction. I'm going to write that a little bit more formally. So suppose A were a knight, then A is telling the truth, and A, B, and C are knaves, because that's what A said. But A cannot be both a knight and a knave, so we have a contradiction. And what does it mean when we have a contradiction? It means whatever we supposed at the beginning must be wrong, because this is the only thing we guessed on. Everything else followed logically. So we say, suppose A were a knight. We don't know. We're just guessing. Then, if A is a knight, he must be telling the truth. And if he's telling the truth, then A, B, and C are knaves. Right? So this next step follows logically from the first. So if that step, or if this logical argument leads to a contradiction, then we know that this first thing that we said must be false. So this is false. Well, what does it mean if that's false? It means the opposite is true, and there's only two choices. He's either a knight or a knave. So, running out of space here, we can conclude, therefore, A must be a knave. Right. So we've solved part of this puzzle without even looking at what B said. Now, B says exactly one of us is a knight. Let's think about this on the next page where we have a little bit more room. So, we know that A is a knave, right? So now we've got B and C that we don't know. So once again, I'm going to make a guess. And I pick my guesses in ways that I think are wrong, even if I don't really know. So I'm going to guess, because I find it easier to contradict it that way. If you guess right, then what you're going to find is everything works out beautifully. But it's always a good idea to check, because what if two different ways work out beautifully? So I always like to check both sides just to make sure that I'm sure about my answer. So I don't really know if B is a knight or a knave, but he's saying that one of them's a knight. I think it's going to be easier to figure this out if I guess or suppose B is a knave. And as I said, we could do this either way. So let's do it two ways. Suppose B is a knight. Well, so if we suppose he's a knave, then what does that mean? It means that he must be lying. So we're on this side over here now. So if he's a knave, then B is telling a lie. Remember, every statement is either true or false. So if this statement isn't true, it must be false. What does it mean for it to be false? Well, he's saying exactly one of us is a knight. So to be false, it would mean either none of them are knights, or what's the alternative? We already know that A is a knave. So the alternative is that both B and C are knights. Because if it was only one, B or C being a knight, then B would be telling the truth. But we're supposing that he's a knave. Okay. Now the problem is we've got these two choices. None of them are knights, or both B and C are knights. The problem with the first part is that if none of them are knights, and we know that A is a knave, A would have been telling the truth. So but we know A is a knave, so that's not possible. Let's look at the other idea. Both B and C are knights. Well, the problem with this one is we supposed that B was a knave, right? So we can't deduce that he's also a knight. So we have our contradiction, right? Because we said that there's two choices. If he's a knave, there's two choices. Either none of them are knights. Well, we disproved that here. Or B and C are both knights, and we disproved that here because we found a contradiction. What this means, our initial statement, right, our supposition right here must be false. Therefore, B must be a knight. Right? So let's see what had happened if you'd guessed the other way. If you said, suppose B is a knight, well, then that means he's telling the truth and exactly, so then B is telling the truth, which means he's the only knight. And A and C are knaves. Okay. Over here on our first side, where we suppose that B was a knave, we don't know about C yet, but we did conclude that B must be a knight. So in both of these cases, we've concluded that that B is a knight. Okay. So at this point, we have A is a knave, B is a knight, and similarly to this step over here, if B is a knight, then he's telling the truth and he's the only knight. All right, so since B is a knight, then B is telling the truth. So therefore, C is a knave. So from these two rather simple statements, right? They're not going into a lot of depth, and it might seem at first like there's not enough information. But from these two, we've figured out that A is a knave, B is a knight, and C is a knave. And the way we did this, as I said, if you do it directly, if you guess the right way directly, well, you get the answer, which is great. But even if you don't guess the right way directly, we still got the answer. And we did this via a proof by contradiction, right? And the way a proof by contradiction works is we suppose something, and then if we run into a contradiction, we know that the thing we supposed is wrong. And since whatever we suppose is a statement, it means it's only true or false, which means the opposite is true. Okay. So, by using two proofs by contradiction, and I put proofs in the little the little quotes, because we weren't really proving anything. In this example, we were solving a puzzle rather than proving the answer, but it amounts to the same thing. See, we used a proof by contradiction here as well. Or we supposed something and resulted in a contradiction, which let us know the opposite. So we've done this twice. We have two proofs by contradiction. We know the answer. So let's formalize this notion of a proof by contradiction. So the way a proof by contradiction works, first of all, in Latin, proof by contradiction is known as reductio ad absurdum, which quite literally means reduction to absurdity. Right. What we're going to do is we're going to take whatever we're trying to prove true, and we're going to suppose that it's false. Right? What does this mean? This means we have to assume the negation of the statement is true. Well, recall the negation. If we're trying to prove a universal conditional statement, that's what we're trying to prove true, we're going to suppose it's false. Well, what's the negation of that? If you recall back to Module 2, the negation of this is an existential statement. Such that, remember, there's no implication in the negation. It's just P of x and not Q of x. So we're going to suppose, if we're trying to prove that something is true for all elements in a domain, that P of x implies Q of x, we're going to instead suppose that there exists an element in the domain such that P of x is true and Q of x is false. Right? And then our goal, how we're going to do this, is we're going to show that assuming that there exists an x in the domain such that P of x is true and Q of x is false, we want to show that this causes a contradiction. Right? Which means the negation cannot be true. And as we know in that's listed out in step 3, if the negation cannot be true, then the statement must be true. So let's see a numerical example of this. We've seen a couple of these examples with the Knights and Knaves. Let's look at a numerical example here. So we want to use a proof by contradiction to prove that if 3n plus 2 is odd, then n is odd. So we noticed here the first step is we want to assume the negation. In order to assume the negation, I'm going to sort of break this into 2 steps. First, I want to write it as a universal conditional statement. And then I want to figure out what is the formal negation to that universal conditional statement. So I'm going to say this formally. This can be written as, well, if 3n plus 2 is odd, then n is odd. Let's do this as for all n. We could say for all integers n because that's really implied in the problem. It's not required, but it's optional. For all n, if 3n plus 2 is odd, then n is odd. Well, again, recall the negation of a universal conditional statement. It turns it into an existential statement, and now we no longer have an implication, we just have an and. So the negation is there exists an n such that 3n plus 2 is odd and the opposite of the above. And what's the opposite of n is odd? It's n is even. You could also say an n is not odd. Okay, so we have our formal statement. We want to suppose that this negation is true. So I'm going to start this. The proof really starts here. These are just sort of me writing everything out formally. And I'm going to call them step 1/2. Or step 0, that's better. Step 0. Okay, and now I'm going to say, what kind of proof am I using? Proof by contradiction. Direct proofs are the default, so you don't have to say proof by direct proof. But with every other type of proof, you need to be specifying what kind of proof it is. Proof by contradiction. So suppose not. Right? I want to suppose the negation. That is, so I'm supposing the original statement is not true. And I say suppose not. So I say that is, suppose there exists an n such that 3n plus 2 is odd and n is even. All right, so that's step one. Okay, if we look back at our steps, the next step is we want to derive a contradiction from that assumption. Well, I'm just going to start playing with it and see if I can find a contradiction. So one thing I'm noticing here is we're supposing n is even. What does that mean? Well, since n is even, we know that n equals 2 times k for some integer k. Right? That's by the definition of even. Now notice there's two parts. We're supposing n is even, and I'm supposing 3n plus 2 is odd. I strongly recommend, in fact, there may be exceptions to this occasionally, but 99% of the time, you want to pick one of these to start with. You do not want to start with both. This is the same as the logical fallacy where you set two things equal and you walk down. We're trying to find a contradiction. It's going to be easiest to see if we start with one of these and go to the other. Now, we could have started with either one. I try to pick what looks simpler, so n being an even seems simpler than 3n plus 2 being odd. But we pick one, and then we go from there. So, since n is even, we know that n is equal to 2k for some integer k. And now we can plug this in. So, what does that mean about 3n plus 2? Again, I'm not saying this is even or odd, even though that's part of our supposition. I'm just going to say, well, if n is equal to 2k, then this is going to be 3 times 2k plus 2, right, by substitution. Well, what does that equal? That's going to be 6k plus 2, and that's just by multiplication. Well, what can I do with that? I can pull out a 2. Okay, I'm running out of room, so I'm going to go to the next slide. So what did we have here? This is a continuation, but we had that 3n plus 2 was equal to 2 times 3k plus 1. Right, that's, we started with 3n plus 2, and we concluded it's equal to 2 times 3k plus 1. Well, why don't we let some new variable, let's say q, equal 3k plus 1, right? And that's the principle of existential instantiation. If something exists, I can give it a name. Okay, so what do we know about q? Well, we know that's an integer. For example, y, due to integer closure, well, what does that give us? Well, then we know that 3n plus 2 is equal to 2q, where q is an integer. Well, that's the definition of even, that something equals 2 times some integer. But here's my contradiction. We said that 3n plus 2 was odd. Right? And here we've shown that 3n plus 2 is even. So this is a contradiction. So I'm going to put it like this. Contradiction. It's really important that you point out the contradiction. It's not a proof by contradiction unless you have a contradiction. And if you have a contradiction, you need to say that you have a contradiction. So we made an assumption that the negation was true, right? We supposed the negation. And now, following that logically through, we've come to a contradiction. So we can conclude that therefore the negation is false, which means it's true. The original statement is true. Right? And that's what we were trying to prove. We were trying to prove that that original statement was true. We were trying to prove that if 3n plus 2 is odd, then n is odd. And we supposed the opposite. We supposed that for some n, there exists an n, 3n plus 2 is odd and n is even. And we've shown how n being even means that 3n plus 2 is even, which is not what we said. We had said that 3n plus 2 was odd. So we have come across a contradiction and can conclude the negation, the opposite.